Hi, welcome to a little lesson on energy band diagrams and a little introduction to electrons and holes. And like I just said, energy band diagrams, they're a pretty crucial part to understanding how electric devices work, like transistors, i.e. MOSFETs or HEMTs or stuff like that works. A lot of these small devices are characterized by energy band diagrams as shown right around here. First thing you need to know are electrons and holes. So electrons are what you've seen in your physics classes and stuff like that. Holes are a little bit newer. When I first learned this, I did not know what holes were. So the idea of it kind of confused me. So consider it as the opposite of a hole, but that was also weird to me. It's kind of like a water bottle. So think of it this way: there's a water bottle. The water bottle is filled with holes and electrons, as filled with water and air. The water is the electrons, the holes are the air in this analogy. Check up the water bottle, and there's little bubbles inside of the water. These little bubbles are little pockets of airs. And now, if air had no mass, then there wouldn't be any bubbles. So that's the way I think of it. So it's very similar to how holes react interact with the surrounding objects, surrounding atoms in different lattice structures or different devices. So the holes actually end up moving around similar to how electrons do. And the way that people denote holes and electrons in all these equations that we'll see in the future are either E minus or H plus or just E and H, but most commonly that I'll be using especially are N and P. My thinking as to why it's N and P is N is negative and P is positive. That's my understanding of it. That's my guess. I'm not 100% sure why, but that's my guess. And when we're referring to it in general, we call them charge carriers, because they carry charge. Now, next part we're going to talk about is Na and Nd. So Na and Nd are talking about donors and acceptors. An example of a donor is arsenic. So say an arsenic atom put into this silicon lattice would have a positive charge that is held in place and a free negative charge for the electron being carried around and moving freely. Same thing with, well, I guess the opposite thing with acceptors. Say, for example, boron. It'll have a charge of a negative charge held in place, and it'll have a free hole that can move around. And there will be an Na and an Nd, because these are the concentrations of acceptors and holes, acceptors and donors in like a semiconductor. And because this is called doping. So you're doping to change a material's properties. And so you can figure out how you can change materials or properties based on how many donors you have versus how many acceptors you have. There also are multiple types of doping, or say you can put, maybe if you want, you can put a little atom in here to make that type of doping. One doping we'll focus on in this general series of videos or understanding that we'll understand for basic device physics, we'll mainly cover this type of doping. If you want to find the net doping concentration, it's just Nd minus Na, the absolute value. That makes sense. If you aren't familiar with doping, haven't seen it before, for a good reference that you should look for in general is 10 to the 15 to 10 to the 20 is roughly what you'll see. 10 to 15 is pretty low. This is kind of low. It's kind of high. So you'll see somewhere in that range in most problems you'll see in class or in most sheets describing materials you're using. But oftentimes it'll be 16 or 17, maybe 18. That's in general. And the next thing last thing I want to talk about is energy band diagram. So there is three main regions. There's a conduction band, there's a band gap, and a valence band. The conduction band is where you can conduct the most amount of energy. where you can conduct energy really to make it more simple. This is where you conduct energy. This is where the areas are stored. All the charges are stored, pretty much. Everything, all the states in here are filled. They're all empty here. So the electrons or the charge carriers are filled up here, and they want to jump up to here so they can conduct electricity, or conduct a current, or volt, or anything, conduct a charge. What they have to do is go over this band gap. There is nothing in this gap. It's empty. So imagine jumping over a river or a little stream. You don't want to go. There's no land in the river. It's all water. So you want to go from there and jump across. Well, to do that, you need a certain amount of force you got to exert to get across it. For this case, the force is electron volts. That's the unit we're using. And in the future, when we see most of these these energy band diagrams, we won't be including the top layer or the bottom layer. It's just going to be the edge of the conduction band and edge of the valence band. And Eg, which is noted here, is the band gap. So whenever you see Eg, it means the band gap. Ec is the conduction band. Ev is the valence band, its energy level. And most common what we'll be seeing in these series of videos is silicon. Silicon's pretty commonly used. It's pretty ubiquitous, so you'll see it. I mean, it's in most technologies we see now, but also it has very easy numbers to work with because it's most data points for it. And also 1.1 is pretty easy to work with versus something that's like 3.2 or 2.7 or 1.7 or 2.4. Like, these numbers are a little harder to calculate with. 1.1 a little bit easier. So it's for ease and for just amount of numbers we have that are readily available, we'll use some silicon for most of these videos. Next time I'll be working on is density of states. Quick little thing about that we'll be going over in the next video is, as I mentioned, all these states are filled here and they're empty here. We'll go over a quick little graph describing them and then determining where these charge carriers actually are, where the probability is